All right. Hello, everybody. How are we doing today? Any, let's see, I get into the chat here. All right. General mood, how are we doing? Pretty good, pretty well, doing good, doing well. Excellent, excellent. All right. So, you should all be, hopefully, everyone, we're all caught up with the basics of texture mapping. Mapping, a little bit of UV coordinates, a little bit of, perhaps spinning cubes or spheres or um, all those sorts of things. So that's the general idea. Hopefully you found perhaps some dice textures or some images or pictures or whatever you want to use, and use those for texture mapping, basic texture mapping on models. So we've so far dealt with vertices. Now have had things like their actual position, a UV coordinate, and we've talked, kind of hinted at them having potentially their own normals and so on, and how they're going to be used. Now, some of those structures are going to be a little bit more, even more useful as we get into things like lighting. So this time around, we are going to be talking about some additional things inside of vertices and how to create models and so on. But in and of themselves, I think we're going to be pretty much relying on now at this point all the techniques you've had so far, kind of building them into a model sort of structure. And now that's not to say we haven't seen that already a little bit, in terms of, we've had spheres, we've had cubes. So you have been generating models or working with models, or more or less just using things that have been defined in code, as an array of vertices. So yes, they're models, but, they're just kind of hard-coded, literally, I guess that's a good use of the term, hard-coded directly into an array that you've had in your actual C code or your C++ code. So we've been doing it the hard-coded way. I wouldn't say the hard way or the easy way, but the hard-coded way. So for today, I want to talk about two different things. I wanted to revisit a little bit. There were some questions, and this next, I'd mentioned about the sort of the real brute force graphics project that you can sort of have ongoing in the background of things. I didn't want to necessarily put a deadline on it because it's the sort of thing, as you go on, it's kind of, a useful thing as you see topics, as you want to talk about a particular topic or try something out. This is kind of a fun, kind of background thing, which I do want to check in with you. And then at some point, by the end of the semester, see that you've done some stuff. And this is the idea. Let me go ahead and switch my screen here. This idea of, kind of some real brute force approach to graphics, actually handling the rasterization yourself, getting an appreciation for some actual algorithms. So after Friday, I decided to go back and kind of revisit my Bresenham, brush up on my Bresenham skills and see if I could write a really kind of optimized Bresenham line generator along with, some, fancier features. So what I decided to do, I kept the PPM format. Wanted to keep that one around because I think that is, definitely the one of the simplest graphics formats. Literally just with a slight, tiny little bit of a header at the beginning of the file, and then just a triplet for R, G, and B for each pixel in your image. It doesn't get much easier than that, so it's nice and easy to implement. Requires no libraries, anything like that. You can kind of roll your own really, really easily. And then on top of that, I decided, okay, I wanted to create a reasonably complete Bresenham line algorithm in here. So if you consider Bresenham, now let's talk about him just a little bit more, how Bresenham line generation goes. Now I talked a lot last time. It was a matter of, okay, you have a line, and then for each pixel that you're drawing, when you're actually drawing pixels as compared to the calculated line, you have this question of, do pixels that you can potentially draw on the screen they may not fall directly on the point at which you would calculate, for that particular line, right? So you're faced with this notion of having to do some sort of either rounding to figure out, you just round the number and you draw the pixel according to, maybe you have X that monotonically increases as you go across the screen. By monotonically, I just mean it gets, 1, 2, 3, 4, 5, 6, and so on. You just plug that into an equation for a line and you'll get the Y value back, which is probably not going to be an integer, so you have to do some sort of rounding to kind of make it work. But rounding is potentially an expensive operation because it's usually going to be some division and some multiplication and so on. So the idea is, how do you keep track of something, as it crosses these boundaries? How can you do it with basically integer-only operations, and hopefully even avoiding things like multiplication, right? And you do that in the case of Bresenham. James Bresenham came up with a really interesting idea that basically he would keep track, you can sort of calculate once what the pitch and the slope of a line is, or this, so you kind of calculate, okay, for every pixel I move across, potentially I'm going down or up, depending on what direction the line is going in. I can figure out, okay, I add that amount each time I move, right? Because it's always mx, right? So you're always multiplying x times the slope to get the next pixel, right? Is the general idea. So imagine you can just calculate that, you have that slope, and each time you move by 1 pixel, you can add that amount to what you think the y value should be. Now the problem, of course, is that we've got this potential not floating point number, and then again, so we get kind of two things to deal with. We have, potentially we're adding not a floating point number every time we move, but then also we still have the rounding problem if we just use that. But that's kind of one of the foundation points. First you say, okay, well, I know that every time I'm moving along one axis or the other, depending on whether the line line is sort of tall or wide, sort of like if it's, here's a wide line here versus a tall line here, right? In some cases, it makes sense to go according to y, depending on if it's a long line like this, right? It may make more sense. Oh no, that's a good case. Yeah, that's a good case for y, because I want to calculate 1, 2, 3, 4, 5, 6, and then figure out how wide it is. Whereas if it's just sort of diagonal, it doesn't matter each one. But you have to think, first you have to identify it to say, okay, where is it always increasing by 1 and not repeating, right? So in this case, if I just scan this red line here, hopefully you see that red line, I can see, okay, as I move across 1, now I have to make a decision. So y is kind of going to be changed here or not, or here y is changing or not. So this makes sense to kind of move by x and then evaluate to see, okay, should y change? Should I, do this one? Should I increment? Sorry, I keep getting this backwards again. Should I increment x yet? Right, in moving across here. So x is sort of repeated, whereas y is not. Right, there's a distinct value for y along each one of these, but x here, x has 2 values in it, 2 values in it, 2 values in it, right? Right, because x is across this way. Whereas in like these, x always has a single value in it, whereas y, the same y value is used for both of these pixels. Maybe that makes a little more sense, right? So you have to make a sort of decision whether it's a steep or shallow line to figure out, does it make more sense to evaluate 1 x at a time or 1 y at a time, right? So that's one of the pieces. And then for each time you do move, you say, oh, okay, let me add the slope in. You may have to calculate the slope depending on which one you're thinking about there. But then also, so now we can potentially do that. So the question is, how do we handle this rounding part and the non-integer aspect of it? So the cool thing about it is if we start off in terms of integers, and these lines have just integer endpoints, which they would have on this screen, in this image here, is I could say, all right, there is some finite number, not only finite, but a non-decimal, a integer number that's going to get me from here to here, right? The endpoints, I have some integer x and integer y that I could add to that, right? So if I am clever, I can, for example, if I took rise over run, which would be a change in y over a change in x, and I multiplied by x, multiplied the top and bottom by x, I could effectively, or just multiply that, yeah, top times x, I could get rid of the denominator as long as in the other subsequent calculations I am doing for comparisons, I also multiply them by the same amount, right? We can always kind of multiply by the same amount if we're just doing sort of comparisons, right? If I want to compare is 1 greater than 2, and for some crazy reason I decided to multiply both 1 and 2 by 3, if I multiply them by the same number, the math, the comparison is still the same, it's just the math gets scaled, right? So that's sort of a common theme you'll see in a lot of places where you're trying to substitute integer-based math for decimal math. Sorry, I'm kind of going a little bit on a tangent here, but that's one of the techniques you'll see a lot in Bresenham line algorithms. All right. So throughout an implementation, you might see a shortcut like that to say, oh, okay, you know, I'm comparing this slope, but what I'm going to do is I'm going to actually multiply it by the denominator, so I can use, you know, just the rise or just the run in my comparisons, so I don't have to have that that decimal term in terms of my calculation. And then the other piece of it, as you move along, the other thing that normally you need precision for is as you move from piece to piece here, from x to x to x to x, is that normally if you were adding a value in, if you are using enough precision in terms of floating point, you don't have any error. But if you don't have much precision in terms of floating point, you have to worry about kind of error creeping in. But we can use that to our advantage in that if we said, okay, each time now when I move from here to here, I can keep track of some sort of accumulation of how far I should have gone up, but maybe did or didn't. And then the next time I move, I increment by some amount, and so on and so on and so on. We keep track of a threshold that is either above or below the line, and then readjust that amount each time we move from piece to piece, right? So we're kind of keeping track of this sort of running count to see when do we cross a boundary that allows us to say, ah, yes, this pixel is above or below the center of the line, or which one is nearest the line, right? When have we actually crossed the line? And this notion of accumulation and this kind of hack for rounding forms the basis of a lot of different algorithms in simple kind of pixel-based graphics, right? So we can keep track of things, and we add, okay, what add in the slope each time, but we have it calculated. Then we say, okay, did we cross a boundary that would make us basically know that we have crossed more than halfway through that line? Okay, we better draw that pixel. And then if we see, okay, now we move along, we haven't moved far enough to say, yes, we've moved halfway past here, we have to draw the same pixel again. And then we accumulate some more, and then we say, okay, we've now crossed that boundary again, now draw that pixel. So sometimes we're making a decision, do we move along the line according to the slope, depending on whether we've kind of crossed these thresholds that we're using, right? So if you do look up a Bresenham line algorithm, you'll see that that's really the basis for it. Now, and I hesitate, this is always the tough thing. The moment I say, okay, let me show it in some code here, is the moment like everyone would just pause the screen and use that for their example. But I guess I could show a little bit, because I was very proud of this. This is in under 100 lines. The actual algorithm itself here is about, so the line drawing, I've done it in 94 lines, fairly well spaced out with extra, kind of cool looking things. And okay, you've already screen grabbed or shot whatever, or paused the video and to see how exactly I did this anyway. So there's this notion of stepping through a line. You see here's like the guts of one of the versions of it where I say, okay, I start off, I draw a pixel, and then I accumulate my slope and see, does it cross some boundary? And here I'm able to use 0 because I've kind of calculated that in. And each time I cross that boundary, I subtract the next target from it. So I can always do my comparisons to 0. So I always have this accumulator that the moment it goes past 0, I know I've moved in the direction that the line is moving, right? And you'll see, so I've got basically part of the rise, part of the run happening sort of in here. And I won't go into complete details there, but the fun part about Bresenham line algorithms is it's always, it's one of these fun, challenging, how few steps can you do it in? How few special cases can you do it in? It's one of these kind of wonderful challenges. And a lot of times you see on the order of 4 or more special cases, depending on the angle of the lines, kind of the direction of the lines. Is X, did you give it a pair of pixels where the first pixel is the low pixel, the first pixel is on the left, the second pixel is on the left, and all these kind of special cases. And you'll see lots of interesting implementations. So I'm very happy with this one because I managed to nail it in 2 cases. One, if it was basically an instance where where X is increasing faster than Y, or is Y increasing faster than X, and then handled all of the different directions and angles and cross points and so on within just 2 other cases, given some clever tricks with incrementers and so on. All right. So I don't want to go into too many of the details on there, but that's the sort of idea behind the experiment, right? I want you to get the feeling for the experiment here is really to try something out. Find a known algorithm, the basic explanation of it. Maybe you need, even a little bit more of an explanation than the piece I've given here. Finding one where it actually kind of lays out the argument, maybe a circle algorithm, or revisit Bresenham again, and then say, okay, give yourself a simple, like here I've given myself a very simple image buffer that's 64 by 64 and potentially RGB and maybe even A in it. So I gave myself a really, really simple pixel buffer, and then I allowed myself to kind of draw pixels into that according to some algorithm. At the end, I have a right image that wrote it out, so I can then see what was the results. And from there, you can then start to build on that. So I could certainly add circles, and I did this version so I could just add lots and lots of different lines. I could draw some random test to see, okay, I generated 10,000 random dots just to see, okay, is it going to crash? What's the result? If I generate 10,000 random lines, what happens? What do you think is going to happen? Somebody tell me. Somebody ask. What will happen if I draw 10,000 lines in just random from 2 random pixels to 2 other random pixels? No one wants to guess? It's a pretty simple. Pretty much. Unless I'm very unlucky. Now, given that there's, let's see. So we have 64 by 64, which means we probably have less than 10,000 pixels. So if I draw 10,000 lines of random length, one would hope that it would actually fill the image. So let's do this. It's a great way to have a test. If you're not sure you could generate every possible case of something, this is a good case of let's test our code. So let me close that and open up. Sure enough, there it is. So there's the version with 10,000 random lines in it, all that are within the boundaries of this image. So I feel pretty good about my implementation, right? Because chances are 10,000 random, lines. And it's good to check it and make sure don't just assume that the 10,000 random lines were random until, you do this as well. I've seen people test code where they say, okay, we're throwing tons and tons of random information at this and it didn't crash, so we know it works. And they never really looked at the results, and it turned out that their random number generators were not random at all. and just kind of kept repeating the same values over and over and over again. So they really didn't test their algorithm anyway. So, well, yet another little side segment about about kind of software development and testing in general. It's always good to have a good testing regimen, in terms of figuring out what's going on here. So let's, I'm going to dial this way back here, and whoops, let's see. Let me get my Visual Studio back up here, and we'll just to prove that it's not drawing also nothing but purple screens. Let's do this. So all of my cases here, go to Krita again, and unfortunately it doesn't automatically refresh, so I have to kind of close this image and then open it again. So there it is with 10 random lines, some that are kind of steep, some that are kind of flat. So this is going down, that one's going up, that one's that way, that one's going that way. So I'm pretty convinced that they're doing lots of things. Other things I added in terms of testing overall, I wanted to make sure, okay, what happens if I have horizontal and vertical lines? What happens if I have true vertical lines, or diagonal lines, excuse me, true diagonal lines? I want to make sure of that. And then I also even have this special case down here, this one purple dot at the very, very end. And the reason for that is I want to see, well, what would happen? Is there any degenerate case that a single point, it's the same there. I want to be able to use this same line drawing algorithm. It's very inefficient if I did it this way, but if I gave it just a single point, that should work as well. Okay, so that's the sort of testing I go through when working on an algorithm like this. So if you're working on a game engine or whatever, it's good to kind of, come up with some sort of test suite that you can convince yourself that you're really, really kind of testing your algorithm. And this is really fun to kind of make sure, do I have all of the cases sort of taken care of? Now, one other thing which I did in here, which is now not completely obvious to you now that we've drawn this purple over here. The next case, what I decided to do to even make it more interesting, is I added this case where the lines themselves, I didn't do any anti-aliasing. You'll notice these are what look like to be gray lines here. Right, these there's a white line, a white diagonal line, and then there's two gray diagonal lines around it. But you'll notice in the center here, other than we have those kind of weird green lines also kind of crossing over, it didn't just go like gray straight through things and so on. So why is that? You'll notice here, like, okay, this is lighter gray, this stayed white, this stayed white, and so on. And that's because I decided to add in alpha channel. So any of these lines can actually be drawn with an alpha channel, which is why this dark blue line here, as it crosses this pair, I have a light blue because it crossed white, and then kind of that same medium blue here, a little bit brighter than blue on black, because these are actually a brighter blue with an alpha channel throughout. All right. So that's my little project that I'm going to use as just sort of a playground throughout the semester for things sort of in the back of my head. And if I see an interesting algorithm, I'll kind of share that with you. Maybe I'll draw circles and so on. But I want you to go through the same exercise. And by the time we get towards the end of the semester, or as we do the check-ins and things, let me know when you have something cool there. But I do expect you to have some of those along the way, and I'll kind of offer up some ideas on that and cover little algorithms in class from time to time. All right. So any questions or thoughts on that? So I'll type any questions or thoughts on the sandbox project. We'll call that one the sandbox project. All right. Nobody's chiming in, but maybe some typing. That's good. What's it worth? I guess that's a good question. So I'm not going to turn this into a whole nother project and re-change the grade. So I'm going to make this part of sort of the homework check-in grade, right? Now, okay, Anthony, very good question. Is it possible to use something like this to generate a bunch of random textures? Ding, ding, ding. Absolutely. The question is, and maybe not at all random. Maybe you want to design textures, or maybe you want to, draw textures, right? So here's a good case. Imagine in your project you wanted to have a little window open, and then you were using, so you were using IMGUI or the mouse and so on to draw a texture. And maybe you wanted to not just draw pixels, but actually draw lines. So you could use this little sketchpad idea to have a buffer in memory to kind of do some primitive drawing and then use those as textures. So we'll have to figure out, or you'd have to figure out exactly what formats, once a texture is loaded into something. Now, the way that we're doing textures with soil and the most examples right now is we kind of bypass the buffer and we don't really see or manipulate the buffer. So that would be an extra step, certainly worth looking into and worth credit to figure out, okay, how do I, rather than load a texture from disk or from a file, instead, how do I create a texture as a buffer and put that into another texture or into a texture. Now, there's also circumstances sometimes where you're going to want to take and render stuff from the screen, render that into a buffer, and then use that as a texture for something else. That sort of layered rendering and rendering to textures that are then used as textures elsewhere is used actually quite often in doing things like reflections and skyboxes and environment mapping and all those sorts of things, where you say, okay, let me generate the world around to some degree, and then I'll use that as maybe an interior texture or a reflection on a window or things like that. So this is kind of a fun little side way to kind of consider that. So if you can generate your own textures, draw them in, that's potentially cool project. But kind of put one of these together, find a simple ppm hint on that. Again, it's really as simple as figure out what the header file format is, really simple, and then just write the values out. So you'll be checking on your check-ins on that as things go. All right, enough on that. So there's Bresenham yet again, my attempt to kind of explain it and my own kind of fun optimization of it, my two-case incrementer operation and the alpha channel on lines. All right. So let's move back on to talking about, whoops, let's see, I don't want that, close that. So let's talk about 3D models. Okay, 3D models. So in the case of the next couple of examples here, now normally, I'm sure you've all seen 3D models. The concept isn't new to you. Like I mentioned before, sometimes you have, simple primitives that are just built into your programs that you just use as is. Other times you have models that might be built from a number of different things. So let's show a couple quick examples. And the idea is that, the chapter 1, the first example is going to be this sphere with the world map mapped to it. It is not animated. Neither of the samples as written in the book are animated. I would challenge you to, whenever you do load a model, do something with it, animate it, make it rotate, make it do something. Who knows, you might discover bugs that way. So, for example, here, I would ask in this next one, I'm going to run this, and I took it upon myself to add this rotation, and this will be proof that you actually went through everything. Animate this donut and tell me what's wrong with the text's code for it, because the text has some bugs in it. So I'll leave it at that. There's the challenge. All right. And throughout, if anyone finds, I give bonus points for anyone finding a bug in the text's code as long as it's reproducible, from my version that's also taken from the original text, that's worth a point or two for homework or something along those lines. But yeah, this was a fun one, and there is a bug in there. Anyway, it's not obvious if you don't animate it. And last but not least in here, I'm going to talk about the notion of a real model. Okay, really having a model. So here's a space shuttle that is a wireframe or a normal polygonal model, and then it looks way more detailed because we have this wonderful texture all around it. So let's start taking a look at some of those directly, though. All right. So the two ideas, basically, and this, well, I guess you could say three here. Models can be built procedurally, externally, or I'll add one more, explicitly. Okay. In the case of just if you've got the vertices of a cube like we've done so far, that's sort of an explicit modeling. Okay, we just said, there's the we've calculated the values and there they are. There's sort of a procedural aspect to it, so maybe it falls into that category being procedural, but we've kind of explicitly specified the vertices, just hard-coded things in there. But in most other cases, we're going to be talking about procedural or algorithmic generation of models, where we specify the math behind the 3D model, or we load in something externally through some format that has already been created. And who knows, maybe that other program is also doing things like procedurally modeling. Maybe you're using everything from graphics primitives to metaballs to spline curves to whatever sorts of mechanisms you want to use in your other program. But ultimately, the other program like Blender or Maya or Cinema 4D, any of those things, they're creating the model, and we're going to load it into our program. So we consider those to be external to our program. So the first example in the book is procedurally modeling a sphere. Okay, you could also, if you wanted to procedurally model a cube, I suppose you could do that, or any number of other shapes. You might want to consider taking this, and rather than just say, the code in the book is going to show you how to do a sphere and also how to do the torus, how would you do something that was more like egg-shaped or elliptical or a lozenge or any of those sorts of various things that we can express in terms of some equations, some math? You could potentially do that. It'll be very similar, right? The idea is to have, first off, we have some sort of model where we say, okay, the equation of a sphere, we can figure out any particular point on the sphere. It's just, the radius, and we have the angle to help us figure out the point at that particular angle along the surface of the sphere. And then what we do in this case, we do in most cases, we have some kind of slicing algorithm that we kind of go through, right? We want to create these kind of swatches or slices or portions, bands, they go by lots of different names, of the model that we can kind of then attach together. Now in the case of a sphere, if we look at it, it's really just an infinitely varying stack of circles, flat circles, right? We just kind of stack them up and they all vary in terms of their radius. But if we stack them, in decreasing radii, as we go to the top and then decreasing as we go to the bottom, we're going to wind up with this sphere, right? So in some simple cases, we might, create the simplest case at the top where it entirely collapses down to a single point. So that's the single point that defines the band at the top of this sphere. Then we have another slice, which is further down, which we can, kind of plug in our equation, just to figure out, okay, well, let's draw a circle. So if they're all 2D circles, wouldn't it disappear if you looked at it from a certain angle? Well, no, because what we're going to do is we're not actually just looking their faces. The faces, we're not doing that. We're just generating the vertices that way. And then it's up to us to kind of connect the vertices so that we have patches across. So, for example, let me pull up my Epic pen here, and I can do a little drawing on the screen, if all goes well. Here we go. All right. So, in this case, imagine we have Whoa, that's not good. That's really a fat pencil here. How did that happen? There we go. Too fine. Too fine. There we go. That's better. Okay, so this circle, we have 4 points. This one, this one, this one, and this one. And for sake of argument, just to make it simpler at this point, let's consider the next circle down here, which is this one, defined by these, right? So what we do is we define triangles that help us define the surface for that that particular area, or to cover our sphere. So we're always going to step through things after we've created these meshes, or these circles, these slices. Then we have to connect them up together, right? So this is why it won't disappear, because we're going to create something that connects each of the vertices and create some, hopefully, minimum set of polygons that will cover the shape, the set of vertices. We're going to basically, it's called skinning, right? We're skinning this set of vertices here that give us this, hopefully, watertight or airtight, however we refer to it. Usually we refer to it as being watertight. Yeah, it's modeled in a watertight way. So we wind up creating that. How you do it? A simple algorithm there as well. If you just have, a circle that has 4 points on it, and then another circle, imagine it's the same thing as if you had just a cylinder. So we have to just collect this one to this one, this one to this one, this one to this one, and so on. And then now we have basically rectangles, and we can just kind of divide, and so on, and so on. All right, to kind of cut these things. And usually, yeah, that winds up, pardon my crude drawing, but that's the idea. Right, we can come up with a simpler algorithm than to connect the vertices from slice to slice in such a way that we wind up with all the triangles necessary to show that. So let's take a look at that. Let's see how that really happens. So let's do that. And we'll go over to our examples here. I'm just going to pull a line of code. Whoops, sorry. Phone ringing. I don't know anyone from there, so we'll assume that was a spam call. Now here's where something comes in awfully handy. And so let's take we'll start with our sphere. And we'll look at the code for our sphere. Not what's going to generate the sphere, but the actual drawing piece. And I want to look at the display piece. I'm going to put one line of code in here, one wonderful little line of code, right before the draw arrays function. And I'm going to set the polygon mode to line. Okay. You can set GL polygon line front and back to GL line, or you can set it to GL fill. Okay, so that you can draw the edges of the triangles if you want. It's a simple way to do kind of wireframing. All right. So here is our globe, textured but wireframed. Right. Unfortunately, this doesn't have spinning on it. But you can see now we have created the sphere, and it's a set of, if we just look at it, each slice here, they're uniform all the way up, and they collapse as we get towards the top. So let's do some spinning on that just to see a little bit more of what's going on. And this is going to reveal the thing that I didn't want to reveal, hopefully. Let's see. So we have the model, right, display. And we're calculating the model matrix up here. We're doing a translate, And I thought somewhere we were doing a rotate. Let's see, is there a rotation here? No rotation. So we'll do a quick rotation here. All right. So if we want to do a rotate, okay. So what we need to do a rotation is we need an angle and an axis, right? So I'm going to do right here is I'm going to say first off float current time. So that's going to be my angle in radians. So it's just an increment over the course of time. So real simple rotation there. And over here, this is going to be my axis. And this isn't a particular, I just grabbed whatever. So let's give it an axis here, 0, 0, 1. So we're going to rotate around, effectively around the y-axis, right? So it's sort of a quaternion move on my part here, right? We're going to have this matrix and, well, let's do that. So that we're rotating the material. So we have a translation, then we have a rotation. Hopefully I did that the right way. And now we should have the sphere sort of tumbling, if I did this correctly. Or, well, not tumbling, rotating. There we go. All right. So it's not really the direction I wanted it in. Why? Because I wanted to see what's going on at the top and the bottom. That's really kind of the interesting part of the sphere at this point. And you'll notice, let's see, if I stop it, as it's rotating, I can't get a good look at some of the segmentation going on. So let's change that angle. Instead of Y, let's have it rotate around Z. Real simple. Still not what I wanted. All right, it's always like halfway think this through. I was thinking like X. Nah, it couldn't have been X. Always trust your gut. All right, here we go. All right, so now X is rotating here. Oh, good. I haven't given away the bug here yet. But you'll notice I'm going to try to grab this. And the moment I grab the frame, we can kind of see it's going to pause rendering for a moment. You notice it's based on time, so it kind of jumps immediately. So there, okay, here we go. You'll see that the circles get tighter and tighter and tighter as they approach the pole, right? Until they basically all converge at a single point there. So it's a very naive algorithm here, right? It's not dynamic in terms of how it's figuring out, you know, maybe there shouldn't be as much detail as we get towards the edges of here, right? Maybe we don't need as many triangles here as we do out here. But that's okay. It's just a simple algorithm that just calculates circles and then connects them. All right. So we can also play around with, if we want to get a feel for the algorithm itself. Right now, that's a fairly detailed, fairly smooth model there, right? If you'll remember, triangles all have flat edges. They have straight edges, I should say, right? So we've created sort of a very convincing sphere. Yes, a convincing sphere, even though it has nothing but straight edges. So let's turn that down and say, okay, now each circle is only going to have, say, 12 edges. Right. So if we look at it now, we can see how our algorithm, oh, I guess it does have some special, a little bit of a special case there, I think. I have to go look at that code to see how's it handling that collapsing into just, you see it just has that set of triangles. That last group there I think might be a special case. But it's still, there's 12 segments at the very top and 12 segments all the way around the edge. Right? So we have a much blockier sphere now. Let's take it, say, all the way down and say, well, what happens when we have 4? Is it going to turn into a cube? Not exactly. So for sake of argument, let's turn that texturing all the way back on so now we can kind of see. So we'll turn off polygon mode. And you see, because of the fact that it's trying to divide the top and bottom into 4 parts, we wind up with something that's certainly less than a cube. It has a very cubic feel to it, but it's not quite a cube. Right. And you start to see that, well, yeah, at the boundaries, it does line up correctly, but because of like all of these, generally, we start to get in some errors and things here where the U and V are sort of pinching. Most of those out here, it looks pretty good. I guess maybe just at the poles, the way the texture is kind of together at the top. Maybe there's some bugs in that too. So that's the basics of the simple circle, the sphere, simple sphere. You can see you can go through that example there. Now let's jump back to our model here. So here's what happened. Okay, so we generated these slices, but then around each segment, here's where we group the vertices into triangles, where we create an actual band, a ring, if you will, around each set of circles, right? So we create that band as we move around them. Right? And then as far as texture coordinates, you can imagine if you took those bands and uniformly changed their diameter or circumference, whatever you want to refer to, made the size of each band uniform, flattened it out, you kind of basically create this flattened out texture, which is why everyone loves to complain about the accuracy of the typical map. Because what you're seeing on the typical map is not really the shape of things. It's the shape of things as if they had been sort of stretched out and flattened out as a texture. So, Antarctica isn't nearly as big as that because it's flattened out and stretched to cover it all across the bottom. And, certain things up here appear to be much larger than they are because they are stretched and so on. But if we put them back on a cube, we're basically doing the inverse of the globe problem. We can kind of see things as they should be. Now, one of the things that also happened that you may or may not have even noticed during the calculation of that, we did create normal vectors for the code from the text does create normal vectors. And why is that important? Well, for example, you do want to only draw the faces that are facing out of the model, away from the center of the model. And in our case, we can compute those normal vectors based on, we know the center of the sphere, and we can point straight out from the center of the sphere. That will give us the normal of each vertex, right? A vector that passes through the center of the sphere and that point is also going to be the normal of that vertex, right? So in the case of a sphere, it's pretty straightforward. So we can fairly easily algorithmically or programmatically generate our vertex coordinates, our UV coordinates using our mapping technique here, and our normal vectors, giving this simple math here. And if we look at how the programs actually lay things out now we start to get to see a much more interesting case of using vertex arrays or vertex buffer objects where we can say, okay, now there's a variety of information in there that perhaps is used for different purposes. Now, in here, this first example is basically, you can say, all right, imagine creating slices. You're generating vertices as you go. And you say, okay, I'm going to generate 12 vertices for each slice. Right? They're going to be 12, or depending on how you do it, 11 or 12 unique vertices for each slice. All right, so slice 0 has 12 vertices in it, or 48 vertices in it, however many you want, 4. Then the next slice, then the next slice, then the next slice, and so on. So we just easily calculate those numbers, right? We just putting our disks into our vertex array here. And here's where it gets useful to start using index arrays. This is one of the really good examples of using index arrays, where instead of just telling OpenGL, yep, here's an array of vertices, instead use an array of indices that in each index points to an array in the triangle. Excuse me, not an array, points to a vertex in the mesh or in the list there, right? So to create this triangle, the first triangle, we need 3 vertices. So we're going to give it the index of, maybe it's this one, then this one, then this one. So this would say n times I, that points at that one. N times I plus 1 is that one. N times I plus 1, which is in that next slice, right? So we see, okay, 2 of the vertices of this triangle are in this slice, and 1 of them are in the next slice. And according to this particular algorithm, where they want the next triangle to be the one sitting right next to it, and I'll get out my index pen again for this. This is a good thing, right? So this first triangle, imagine we have, there's our first line, and here's our second line, and we've got vertex, vertex, right? A bunch of vertices here. And here's I, and here's I plus 1 slice. All right. So our first triangle comes from this slice, and it says, okay, it's this. That's one vertex. And the other vertex is this one here. So that means it's going to be that. The next triangle says, all right, this one, and so that's this one here, and the 2 from the next slice, which are these 2. That's how we get that one. And we would do the same thing. 1 from this slice, and these 2. 2 from this slice, and this 1. 2 from this slice, this 1. 2 from this slice, and this 1. Right? So the algorithm we could step through to actually create this band is pretty straightforward. We can do that for the whole set. Right? So we wind up with this array that is going to be, 1, 2, 12, right? That's the first one. And the next one is 12, 13, 2, potentially. This is the indices for this triangle, and these are the indices for this triangle, 1, 2, 12, for that other one. Right, 1, 2, 12, 12, 13, 2. Right, for this one, and then that one. So this is why indices becomes really important. Indexes become really important. Easier to deal with that sort of stuff. An easy way to delete? Yeah, there we go. Anybody have any questions on that one? Hopefully that's a matter of kind of stepping through and seeing how that works. Now let's see. We are at 120. 120. So we are into. We're definitely sort of into potentially check-in time if we wanted to be there. All right. So here's what I described here, this vertical slice here. So we have, each horizontal slice, we get 2 triangles based on one slice and then the other slice. All right. I'll leave it to you to step through the code. Here's the sphere. So we'll take it up to there. So now what we'll do for this week, we'll stop here and say, all right, if you haven't already caught up on chapters 5, which hopefully you have, now kind of step through, take a look at the sphere code, get the basics of that working, try out some of the sort of things that I just did. If you want to start getting ahead to the torus, next time we'll talk about the torus and probably move through, well, you know what? I'm going to leave the discussion of the torus as an open on your own thing. Obviously, it's in the book. The concepts are very similar to doing a sphere. And for next week, or excuse me, not next week, for next lecture, there is the bug that I want you to find in actually both of these programs, but it shows up mostly in the torus one if you do some things. And we'll talk about externally produced models in the next lecture. How's that sound? Is that a good? Is that? Sound reasonable? Now, regarding the project, hopefully, or the project 1, I'm still kind of going through things. Again, most of you, based on our discussion, should have, you know exactly where you were on the project. There was, I think, just one person who was following up on some things to kind of get through, but I haven't posted grades yet. I will post by the end of this week. I like to make sure everybody's all on the same page first, which is why I'm kind of where I am with that. But that'll be by Friday. That'll be all there. Okay, so now here's where it gets confusing. I believe that at least calendar-wise, this is week 6. So we're in chapter 6, week 6. We're doing pretty well in that regard. But I get the feeling that we skipped, we'll be skipping, and that's okay because everybody should be up on this anyway. So maybe this is the fair thing to do, that now we've hopped over here because we'll wind up going back anyway. So I have even weeks. It would be Rich AS3, ORELUS, Aurelius, Hunter 2, Heyo, and NHOP, right? So what I'll do is I will first come around with some texts, and we'll see how that goes. And if I've got extra time, we can kind of pop back in, maybe start talking about the torus some more. All right. Let me see who is around. Looks like people should be around. Yep. Not entirely sure. All right, we're going to stop the lecture piece there. And if you have any questions, do reach out to me. And otherwise, I'll rejoin as necessary here. Remember, everything is on Twitch and recorded and all that as well. One of the things I do want to find out from you during these check-ins is what your thoughts are with regards to Project 2. So that's the other big announcement. Be thinking about that. You should be thinking about Project 2, what you want to do in that part of it. Okay. All right, on to the check-ins.